Welcome, I am Marta Marrón Romera, Associate Professor at the Electronics Department in the University of Alcalá in Spain. The lecture is focused on the electronic support for sensing. This MOOC is developed under the context of Erasmus Plus projects, Graceful Equalizing of Mechatronics students, abbreviated GEMS. So the index I'm going to follow is shown in this slide. I will start with some objectives. After that, the general block of the sensor modules will be described, including transducer and conditioning stage. Moreover, different integrated sensors will also be described, and that is before passing to the description of the characteristics and type of errors in any sensorial system. We will have a final point about calibration of these sensorial systems, and I will finish with some bibliographic references. Let's start with the introduction. Starting with the objectives of the MOOC, we have to tell that it is focused on the understanding of electronics related to generic sensorial modules. The general block diagram of the sensor electronics is based on architecture requirements, calibration, and errors. So all of them will be analyzed. Thus, the MOOC is not focused on analyzing specific characteristics of a sensor and analyze errors related to it. For that, I recommend you to go to the further reading in order to know more. We can now go further into the description of the general block diagram in a sensorial module. As you can see in the slide, and it is described here, an instrumentation system is a collection of different electronic devices that are put together in order to measure physical variables in a specific process. They are really important in order to help engineers to make complex electronic devices. As it is shown in the drawing here, you can see that the different elements in the sensorial system are as follows. Always, the input is going to be the physical variable that acts like a stimulus in a physical system. The physical system at its time converts this into electrical variable, thanks to a transducer. Moreover, the transducer will give this electric variable to the conditioning stage that generates an optimized version of it. This is important in order to be able to do digitalization after that step. The digitalization process will generate data to be processed through a data decision system in a PC or a microcontroller. In this slide, you can see the three main elements in the block diagram of a sensorial system. The transducer that captures and converts the physical variable into an electrical one, the conditioning that optimizes this electrical variable to be processed more easily and robustly, and the digitalization that is in charge of converting the electrical variable into a digital signal to be later processed by the microcontroller. So the key components in the sensorial system are mainly three, as you can see here: the sensor, the conditioning, and the data decision elements. These three electronic elements are the main ones in the sensorial system. The sensor is the one that detects the physical phenomena, the physical variable that is then converted an electrical one. For example, the sensor that gets the temperature in the car, pressure of his tires, or light outside in the road, as you can see in the car in the image down in the slide. Furthermore, the conditioning is the electrical circuit that prepares the sensor signal in order to be processed by the microcontroller. Normally, over there, we find amplification and filtering. After that, the acquisition elements are those that will give digital data to be processed or displayed into the digital system, the car in the example. This acquisition part will be analyzed in detail on next section of the MOOC, so now we will concentrate on the two first elements, sensor and conditioning. Some other key components that are also involved in the sensorial system are the processing units, mainly made by microcontrollers, that take the digitalized data and make decisions, or that at least shown into displays, LCD, and so on. Another important key component is the communication interface, made of protocols and hardware that enable transferring data from one microcontroller or processor to another. Finally, there is a last element that is really important in all the process, and is not studied in this MOOC. It is the actuator. Actuators are elements that act as a result of a sensed variable generated by the sensorial system. We can finally see in this slide three practical demonstrations of different sensorial systems. On its right upper part, we can see the contactless thermometer that gets temperature at a distance with an infrared physical variable and displays it in real time. The second example is the one that you can see in the lower right part of the slide. It is a motion detector element that it implements based on the detection movement of, for example, white animals. Finally, in the bottom part of the slide, you can see a health monitor wristband that is normally used to get, for example, pulse heart rate through a pulse sensor that is shown afterwards in the wristband. Let's now have a deeper view of transducer and conditioning elements in the block diagram of a sensorial system. So what is a transducer? As already mentioned, the transducer is a device that transforms the physical magnitude we want to measure, that is mechanical, thermal, electrical, or whichever, in another one that is normally electrical magnitude. The name of the transducer will be normally according to the transformation it performs. For example, as you can see in the right part of the slide, the photoelectrical transducer converts the light arriving into the base of that bipolar transistor into a current that goes from its drain to its collector. You can also see another example of transducer in the lower part of the slide, where we are looking for a solution for measuring the height of the water in a deposit. There, we will use a transducer that is a potentiometer that transforms the displacement of the water height in a variation of the resistance in the electrical circuit. You have to take into account that the transducer stage is always prior to the conditioning one. We can now present transducer classifications according to different topics. Firstly, we can organize them depending on the type of output variation they give. The detector normally just gives two values, 0 or 1, depending on whether the physical magnitude that is measuring goes over or below a threshold. The sensor, nevertheless, gives as output different values depending on that physical magnitude that is measuring. On the other hand, according to the energy they require to work, we can also find active or passive transducers. Active ones will be those that do not need polarization, as they get power from the signal they want to measure, for example, a microphone. On the other, passive transducers are those that need a power source to work, like a thermistor. Finally, as mentioned before, transducers are always named according to the physical magnitude they measure. Like that, we can talk about thermal transducers, mechanical transducers, and some others. We can even describe the transducer static characteristics, as they describe their performance in permanent regime, or facing small changes in the input variable they measure. It is important to take into account that this kind of characteristics may give rise to fixed error, but those errors can always be corrected through calibration. Both errors and calibration process are described at the end of this video. The basic static characteristics of a transducer are overrange, that is the transducer maximum output that will depend on its power supply, hysteresis, that describes the transducer behavior when facing an increase or decrease of the input sensitive variable, and the repeatability, that is the maximum variation in the output that gives the transducer when working in the same conditions and facing the same input in a repeated situation of measurement. We can then say that in a sensing process, there may be errors giving rise to difference between the output obtained, that is, as shown in the graphic, MS, that is the ideal value, and ME, that is the measured value. Most of these errors can be analyzed, modeled, and correct if they are constant and known through the characterization of the transducer. That will be the calibration of the sensor. In the image, we can see 4 situations for calibration or for modeling. The green line, A, will be the ideal behavior of the transducer, in which MS value is equal to its ideal one, ME. But we can also find situation B, in which the transducer does not behave in a linear shape, or even in situation C, in which we can find this linear behavior, but there is an error of exactitude due to an incorrect relationship between the real and the ideal value of the measurement obtained by the transducer. Furthermore, we also can see situations like D, where we can find an offset that Furthermore, we also can see situations like D, where we can find an offset that has also to be corrected through calibration, because we get a value different to 0 when measuring an input physical value of 0. So, putting this in a nutshell, we can see that there are 8 main parameters to calibrate when talking about statistical characteristics in modeling transducers. Offset, that is the deviation of behavior in the input of a transducer from zero value, the example in previous slide. Linearity, that is a deviation from the straight line in the response of the transducer, example B in previous slide. Sensitivity, that is the ratio of the output quantity to a physical magnitude quantity. And resolution, that sets the minimum variation of the physical magnitude that can be observed at the output of the transducer. Finally, it is also interesting to talk about the response speed, that is the capacity of the transducer in order to give an output as fast as the input is modified. Apart from them, they still are already mentioned the accuracy, that is the maximum expected error in the output of the transducer, the measurement range, in which a certain of precision can be ensured, and finally the error band, that would be the zone around the ideal output where expected error can be ensured as a percentage of transducer full scale. That is assumed and can be calibrated. We can also talk about dynamic characteristics when modeling the behavior of the transducer. Such characteristics describe the behavior of the sensor in the transient period. That means from the moment they start working till the steady state of its output. Over there, we can mainly find three different timings to consider. The rise time, that would be the necessary time for the response to reach from 10 to 20% of its final value. The response time, that is the time that elapsed to reach its 90% in the output. And the delay time, that defines the time that the transducer needs to give the 50% of the output's final value. We can then say that the time constant of a transducer will always be the speed of the sensorial system for a given input to reach its steady state in the output. Now we can talk a little bit about the other part of the general block in a sensorial module, that is the conditioning stage. So what is a conditioning stage? This conditioning block includes all the circuitry to process the electrical signal that the transducer outputs in order to be able to work with it in further stages. The reasons for including the conditioning part at the end of the transducer stage are mainly these two, pointed out here. The first one is to transfer the electrical signal provided by the transducer into a voltage, and the other one is to increase the relationship signal to noise to suitable variables so that the signal can be then processed by a digital system. The conditioning stage, in order to tackle these two questions previously stated, normally include two parts, as shown in the drawing: the amplification part and the filtering one. The amplification is the one that increases the signal power level, and the filtering is the one that eliminates unwanted frequency components in the signal. It's important to note down which part of these have to come first, depending on the type of signal the transducer is giving to the output. You can see here, in this schematic, the conditioning stage in a thermistor that we are using in GEMS. Over there, you can find the filtering stage that is implemented through a passive filter, made of capacitors and resistors, in a blue box. After that, there is an amplification stage that is implemented through an operational amplifier, so it is an active amplification stage. In this slide, you can see we have first filtered the signal to take out all frequencies that are not interesting in the sensorial purpose. And after that, we have included the amplification stage in order to increase the signal-noise ratio in the temperature signal to process it later on the digital part. The amplification stage is included normally due to the small amplitude that the transducers give out. The amount of amplification will always depend on the gain values needed at the output of the sensor. So normally, an operational amplifier is the best option for this function. In the schematic at the bottom of the slide, you can see how the thermocouple transducer is given a differential voltage that is firstly amplified in order to be processed later in the filtering and digitalization elements. The filtering part that we were talking about is normally used to improve the frequency spectrum of the signal that the transducer is giving, preserving valid data and blocking all noise that has been included in the transducer process. You can see in the drawing in the middle of the slide that normally the original signal that comes out from the transducer is noisy, normally of high frequency. So with a filter with a frequency response as the one that you can see here, a low-pass filter, we can obtain a filter signal that is much nicer. and more clean, so that will be easier to later be processed. We can always find two types of filters. A passive one that normally uses exclusively capacitors, resistors, or inductors and gives a maximum gain of 1, or an active filter that uses also passive components but includes normally an operational amplifier in order to give an amplification also at the same time as filtering. So we can now go further into the integrated sensors that we can find in GEMS project. What is an integrated sensor? It refers to a set of electronic components designed to collect and process data from a physical variable in order to give directly a digital signal to be processed in a microcontroller. These systems are completely manufactured to work in a specific environment. That means with a specific communication channel for the microcontroller, a specific functionality and ranges, and errors. In the case of GEMS project, we can find the HCSR04, that is an ultrasonic integrated sensor that will be analyzed further in this MOOC. It is important to note down some other questions regarding the type of errors in sensorial systems that we have pointed out in the transducer section. As we saw, we can find systematic errors and random or accidental ones. The first type refers to those that occur in the same way in all measurements. Over there, it is important to note that they can be caused by a defect of the instrument, but mainly it has to be highlighted that they can be quantitatively modeled and avoided through calibration. If a random or accidental error appears, we have to say that it is normally an inevitable error. It normally occurs due to the unique events that are impossible to model nor control during the measurement process. The bad news about these random errors is that they are difficult to identify. On the other hand, they are small and numerous, so they can modify importantly the signal to be measured due to their accumulation. They normally fluctuate, and the good news is that they normally do it around an average. So they can be defined by statistical methods, normally with a Gaussian process, that can be reduced furthermore in the microcontroller with a digital filter or any other numerical process. To be pointed out also is the concept of uncertainty in a sensorial system. The absolute uncertainty is the error between the maximum and the minimum expected output in the instrument, while the error is the difference between the real value and the measurement one at each time. So uncertainty would be the span in which the measurement occurs. For example, if we measure twice a resistor of 3.4 ohms, we may obtain 3.35 once and 3.41 another time with the same sensorial system. That gives 60 milliohms of difference between the maximum and the minimum measurement. That means that the error has been 50 milliohms and 10 milliohms in each situation, while the range between the two measurements, that is the 60 milliohms difference, would be the uncertainty. As mentioned, we normally statistically model this uncertainty. So we define a probability to expect the amount of uncertainty. For example, if we have a measurement of 10 volts with 10 millivolts of uncertainty, we have to say that 90% of times we will measure these 10 volts. We will have an uncertainty of 10 millivolts in the measurement. Last but not least, we need to talk a little bit about calibration, because as mentioned, it is the way to avoid such amount of errors in the system sensorial that we have talking about. The calibration is important because it is the comparison of the sensorial system reliability with another with the same functionality and known quality, in order to validate, improve, and adjust the measurement that the sensorial system gives. Calibration has to be done periodically in all sensorial systems. And all commercial sensorial systems are subject to calibration regulations due to the European Union in the link included. With that, we will finish with some reference included as follows, used to prepare this lecture. Thanks for watching.